Every private interaction you have online, from bank transfers to encrypted chats, relies on a single technical reality. Certain mathematical operations are functionally impossible for standard silicon chips to reverse in a human lifetime. We secure our data by forcing computers to solve for enormous prime factors, a process that normally takes centuries. But a different kind of machine is being built that operates on entirely different rules. Instead of trying one path at a time and hitting dead ends, a quantum computer uses a property called superposition to exist in multiple states simultaneously. Because the computation happens across all those possible states at once, it processes the entire physical space of the problem in parallel. When measured, the system collapses into the right answer with near total probability. This speed transforms the logic of our security. When a machine can navigate an enormous solution space in seconds, the computational barriers protecting our data simply evaporate. The complexity that currently keeps our information private effectively ceases to exist. These machines are not theoretical thought experiments waiting for the distant future. They exist right now, suspended in cryogenic tanks in active laboratories. In late 2025, Google's Willow quantum processor executed a benchmark algorithm 13,000 times faster than the world's most advanced supercomputer. This is a verifiable, physical demonstration of quantum advantage. And the threat isn't waiting for the hardware to mature. Through a strategy called Harvest Now, Decrypt Later, nation-states are actively vacuuming up mountains of encrypted data, everything from intellectual property to classified communications. They are storing that intercepted data until a powerful enough quantum system comes online to process it. Because of this, our current encryption standards are essentially a delayed release leak. To protect our data, we have to look past math and move toward the physical laws of the universe itself. This is the goal of the quantum internet. Quantum key distribution encodes data into fragile photon states. Due to the observer effect, measuring a quantum system changes it. Any interception leaves a physical fingerprint, alerting the sender and receiver to discard the compromised key. This is scientifically guaranteed security. It makes unnoticed eavesdropping impossible because the laws of physics themselves alert you to the intrusion. Building this new network, however, requires engineering specialized hardware that can handle some of the most delicate states in nature. Qubits suffer from a problem called decoherence. The slightest environmental noise, a tiny shift in temperature, a microscopic vibration, or stray electromagnetic interference, causes them to lose their quantum state, taking the stored information with it. But researchers at the Norwegian University of Science and Technology recently overcame a major hurdle in this architecture. They developed a method to track the loss of quantum information more than 100 times faster than previously possible, allowing for real-time diagnostics. Catching those failures instantly allows the system to run error correction on the fly. This is the threshold required to move these processors from lab experiments into reliable, fault-tolerant machines. Keeping those quantum states intact over long distances was previously a massive engineering challenge. Standard fiber networks could only maintain a quantum signal for a few kilometers before degrading. That changed when researchers at the University of Chicago published a theoretical framework extending that maximum distance to 2,000 kilometers. This puts a continental network within reach. 2,000 kilometers is the distance from Chicago to Salt Lake City. By utilizing repeater stations to amplify these signals without measuring them, bridging continents becomes a reality. This is no longer a theoretical exercise, it's an achievable infrastructure project. In 2026, the focus has moved from proof-of-concept experiments to the practical scaling of hardware. We are seeing the first commercial and governmental deployments of networked quantum systems. There is an urgent parallel race underway. Governments and private corporations are currently upgrading their existing infrastructure to meet NIST's new post-quantum cryptography standards, specifically designed to resist quantum-enabled processing. It is a profound duality. The same bizarre physics capable of stripping away our current digital privacy is the only mechanism capable of building an impenetrable shield to protect it. The core mechanics of global power and communication are being rewritten. The window to prepare is open now, and the transition must happen before our existing computational defenses are finally overtaken.